You know, and you punch them and they bend over backwards, but then they come back right in your face and punch them again. They come back right. I think they're usually kind of clown dolls, right? Or they're made like dress up like a clown.
Yeah.
Sand in the
Yeah.
bottom of them. Here we never like that.
Yeah, continuing the discussion, comment also.
Okay.
No, not comment.
That's fine. We'll start with that. Anyway, there's nothing for these guys in somehow the introduction to my talk anyway. So. You have 2 hands. I would like to have. Okay.
I think they know the introduction.
Good. Yeah. So I can. Yeah. So I can. The introduction. The first, let's say, 10 slides are trivial. So trivial for this audience. So I can try to go fast.
Good luck.
Anyway, at least I have half as many slides as Edmond. So, but, I can usually, given an infinite amount of time, I can approach 30 slides. And maybe 22. So, I chose a pretty broad title because that was a long time ago, and I didn't know exactly who was going to be here and what else is going to be discussed. So, since Edmond discussed after Edmond's and Dionys's talk, what I basically decided to do is that I will concentrate on DIS and on and specifically the DIS impact factors. I have some introduction which is copied from some other talk, which I hope I can go through fast about just power counting and terminology, which of course is a dangerous topic. But what I really want to discuss is NLO DIS with massless works. So a few words about the calculation, which was really Guillaume's, I mean, the way I present it is Guillaume's calculation. I know Giovanni and Jan looked at this before, but somehow the formalism I discuss is from basically Guillaume's calculation, and then we repeated this with especially Risto Haatalainen was the leading author in this paper, where we essentially repeated Guillaume's calculation in a slightly different regularization scheme, which I'm not going to discuss the details about that here. If you want to ask me, I will tell you. And then I'll show some results from the first numerical implementation of these formulas, which is there's no comparison to data and no fit to data. This is something that one is still working on. Then I will just go on to discuss some issues about in a calculation that we're currently working on, which is doing the same thing with massive quarks. Heavy quarks. So this is something that's in progress, and somehow probably there are interesting issues there that I will try to discuss. But these interesting issues don't really have that much to do with small x. They have more to do with how to treat mass in light cone perturbation theory when you do loops. And this has been fun, but surprisingly non-trivial. But I think now I think we understand the conceptual issues. And we already have a result for FL. We're working on getting the full result for FT, which is more work, just more computations. So, but somehow, as a hopefully short introduction, somehow there's this trinity of dilute dense CGC calculations that one wants to do. You want to have an evolution equation, tells you the relativity dependence or energy dependence of the dipole cross section. Using the dipole cross-section that satisfies this evolution equation, you want to calculate the total DIS cross-section, and then you want to calculate single-inclusive hadron production in PA collision, and this was the topic of Edmond's talk. And of course, the essential question is, you really want to do these three consistently in the same framework so that you actually have some predictive power. So Edmond was talking about this, I will talk about this, the DIS cross-section. So the basic starting point is that we do iconal scattering of a target of glue, and and the question is how to measure the small x glue in a high energy nucleus. to do it in a clean way, you want to send the dilute probe through this target color field, and at high energy, the interaction is iconal. It's described by the Wilson line, so the degree of freedom describing what the CGC, the target fluid field, is made of, are Wilson lines which just depend on transverse coordinates, so the boldface here is transverse, which are SU3 matrices. And what often appears is the dipole operator, or the amplitude dipole operator, expectation value of trace B vector B, or the dipole amplitude, which is 1 minus this dipole. And the basic behavior of this dipole amplitude is that at small coordinate separation, this amplitude goes to 0, so that's the color transparency regime. And at large distances, since these are SU3 matrices, there's a group theoretical limit of what this dipole can be. One would expect this dipole to go to 0, and therefore the amplitude saturates. Amplitude saturates in this way. Amplitude normalized in this way saturates at 1. So if you have something that goes from 0 to 1, you know that you can define a characteristic length scale where somehow the behavior changes from being close to 0 to somehow close to 1 of order much more than 1 to of order 1. And this saturation scale, this scale, coordinate scale, is referred to as the saturation scale. So 1 over QS is really the correlation length of Wilson lines in the transverse plane. So how do you do these dilute length processes? So at leading order, you just have a DIS, you have the dipole picture of DIS. So gamma star fluctuates in the equilibrium dipole, which interacts with the target color field. You use the optical theorem to get total gamma star target cross-section as 2 times the imaginary part of the scattering amplitude. And then you have forward hadrons, which is in the picture that Edmond was discussing. You take a quark or gluon from the probe, described by collinear PDFs. You square then the amplitude is given by the Wilson line. The cross-section is given by the square of the amplitude. And when you square the amplitude, you have a dipole. You have a dipole which consists of 1 quark in the amplitude and another quark in the complex conjugate amplitude. And then you do independent fragmentation using fragmentation functions. And this is somehow the hybrid formalism. And the essential thing is that both involve the same dipole amplitude. So this is what gives you predictive power. You, let's say, fit data in one, and then you calculate cross sections for the other. Okay, so this was what for the purpose of this talk, called leading order. Then what I'm kind of following Guillaume's terminology here. What happens at leading log is that you take these processes and you add 1 soft gluon. So you add a gluon here, so this is just one of the many diagrams that you consider, and in the forward hadrons you add a gluon, and again this is just one of the many diagrams that you consider, but you're only looking at the part of phase pairs when this gluon is soft, so the plus momentum of this gluon is large, because this region is what gives you a large logarithm, a large log of 1 over XB arcane, and the same large log here, and then in the forward hadron case there's another limit when you have a collinear gluon which leads in the D-glide evolution of the part. Yes, so I'm working in a coordinate system where I always have K plus and KT, and K plus, small K plus is what I call soft, and with arbitrary KT, and then KT going to 0 with a fixed K plus is colloquial.
But true soft would be K plus and KT scaling the same going to 0 simultaneously.
Yeah, okay, so
well, that's a scaling.
that's okay. So this is fine. You can. I don't want to get bogged too much in it. It's a terminology question. What do you call it? What I call soft is K plus 0. What I call K curve to 0, I call collinear. You might disagree on the terminology. That's fine.
So collinear to what? Huh? Collinear to what? There are 2 directions.
Well, collinear to whatever emitted. Okay. So when you add a soft gluon, you get a large log. And what you want to do is to absorb this large log into a renormalization group evolution of the target. Okay. So and this is the RGE that gives this is the decay equation. Okay. So the decay equation is what you get when you remove somehow the soft gluon from the from the cross-section calculation, and we absorb it into a redefinition of the target, renormalization of the target, and this gives you an RG. Okay, so what happens at NLO? So at NLO, you consider the same gluon, you add this one gluon, but now you want to have full kinematics for this gluon, so you're not necessarily assuming that this gluon is soft, but you want to have the exact kinematics. So this is the DI is impact factor, and this is the NLO single inclusive calculation, which is Giovanni, and Giovanni has really been pioneering these calculations. So here, this leading log small k plus gluon is already in the BK log target. So this, so somehow we're calculating, the one is calculating the same diagrams here. So in order to avoid double counting, you need to subtract this in one way or the other. And basically, the topic of Edmore's talk was how to do this in the correct way for this case of single inclusive. So how do you start from a calculation start from a calculation which has this additional gluon with arbitrary full kinematics, and how you subtract the kinematics when it's soft, when it's a small momentum fraction. And I will come back a little bit to this in the context of NLO, on context of DIS. So then the next order is going from NLO to NLL. So next to leading log, what you're deriving is the NLO evolution equation. So this is the equation of Jan and Giovanni. So what you do there is that you consider NLO DIS, and then so we have two diagrams of this order, for example, and many others. And out of these, you want to extract the leading soft log. So again, you're not doing all of these in the full kinematics, but you're doing this in the kinematic where you pick up one log. So there are many diagrams. There are diagrams which have alpha squared and two logs, which is two iterations of leading order BK. There are diagrams which that are of order alpha squared times one log. So these are diagrams that give you NLO BK. And then there, of course, in principle, there are diagrams or there are contributions which are just purely alpha squared without any logs of x. And these would be part of the NLO impact factor, and nobody has calculated. But somehow, this is just somehow trying to set the terminology here. So this is fine. Everybody is very impressed impressed by this calculation. But as we have discussed, there are there's a lot of additional work needed to actually use this for practical phenomenology, and that has been discussed. Why?
You can do it that early, I think in 11. Okay, he was losing.
Okay, maybe that was a running column. Maybe that was maybe. That's right. Yeah.
Then everybody myself.
So the slides are not very somehow polished, so you shouldn't. I'm not too careful with the references. Okay, so this is the way I somehow define the power counting. And what I would want to say about the phenomenology is that currently somehow working, the current status of phenomenology is at leading log. That has been the state of the art since five something years ago. But gradually, one is starting to understand the theory at NLO and NLL.
Sorry, current phenomenology is leading log plus running coupling.
Plus running coupling, fine. Yeah, so I'm not. Yeah, so the running coupling, yes. So running coupling is part of. So the running coupling in the BK is.
Running coupling is actually on the solid footing than all these power counting, because running coupling is a summation you do in the kernel.
Yes.
So alpha and F is summation. Yeah. Then of course you complete the beta.
Yeah. So running coupling, strictly speaking, is something that's beyond higher order than just leading log, and that is.
But
that is
there. Because a well-defined parameter.
Yeah.
It's maybe like that.
Yeah. So exactly, this is why it doesn't have as many issues. So which is not why I'm not really discussing it here. Okay. So of course, what one wants to do is actually move to phenomenology in NLO and NLM. And so somehow there have been works in this direction, but I think it's fair to say that one is certainly not yet, so one certainly doesn't have a full description of data, experimental data really at the NLO and NLL level. There have been some papers, some works, and it's probably not a complete list, but for example, Edmo and also Javier Albacete did fix the VIS data with this the kind of approach that Dionysius was discussing yesterday, with which I would say an approximate NLO evolution, trying to capture the dominant parts of the NLA evolution. But this is not NLO in the sense of having NLO impact factor. There's also single inclusive hadrons at NLO, which was what Edmond was discussing about, but this is not really, I mean, at least the phenomenology, at least actual plots are not NLL. In principle, I think Edmond would say that we know how to do NLL here, but
Dionysius discussed yesterday, you don't know that much.
Yes. So anyway, I think it's fair to say that there are calculations at NLO, but not really at NLL. Heikki has performed the full NLL numerically solved the full NLL evolution, including the version of this, the 2015 version of the resummations of the BK equation. Of course, that's not comparing the data because this is just solving the evolution equation. But this is not yet NLO in the sense of not yet having an NLO impact factor actually calculating data in the full NLO. And also what I will discuss next is the calculation of the NLO DIS cross section, which is not yet NLL in the sense of having an NLO in the sense of having the evolution equation.
So what can you calculate in the fragmentation region of the hydrogen projectile? Can you calculate the average PT and the average rapidity shift from as a function of energy?
Yeah. So if you calculate the full forward, if you calculate, yes. So if you calculate the full forward single inclusive particle cross section, I mean, getting the rapidity baryon stopping the rapidity shift is just taking that distribution and waiting and integrating it. I don't. I mean, Yasin was looking at this long time ago when he was still in Heidelberg. Yeah. The last actual calculation that really produced curves was, I think that I know of, was Yasin with Wolshin.
Very interesting to know the average PT.
Yeah, it's negative.
For the for varieties.
The PT averages aren't very good because if things go like 1 over PT the fourth, if you weight it by PT squared.
I want to weight it by PT.
Just PT.
I want to weight it by PT.
Okay.
But I thought you were going to tell us next week.
No, I just you guys have done real calculations. I do cartoons.
Larry is doing the same thing in a very different Lorentz frame. And of course, you want to compare to what has been.
I'm interested in the space-time distribution. That I'd like to know kind of as a rigorous controlled calculation how well you can do with average PT, not PT squared because that was a problem. That's totally a problem. But average PT is the question you can ask about. And the average rapidity shift of the fragmentation region particles function energy.
Yeah, so
those are interesting things for all sorts of reasons.
Yeah, that's a straightforward calculation that should be revisited. The last person who was looking at this was Yasin already more than 10 years ago.
But you can take your cross section. Right?
Yeah. So you just take the cross section and then you integrate. Weight it with something and integrate. So it's straightforward.
The other question Larry is asking the average X.
Yeah.
Variable, right? That's a shift.
Yes.
One,
but basically, the average X.
Well, it's a log of X, I think,
so,
you're talking about rapidity.
Right.
Rapidity, but still.
Well, it's very important. If you weight X's, that's not going to be good. That's too strong. But logs of that X have good things to it.
I mean, what you think should happen is basically there's going to be a rapidity shift, which is quite significant, and that's really a big deal because the particles have a high PT also, so it's really hard to shift them. You really move a lot of momentum around the fragmentation region, and that has consequences for things like plastic ray.
Oh yes. I mean that's certainly yes. Okay, so let me go to BIS. So to be specific, what we want to calculate is the total gamma star target cross section for a gamma star which has either transverse or longitudinal polarization. We're using the optical theorem, so I just copied this from some Christos notes, which has these imaginary units, so of course you must be careful with these. But anyway, one uses the optical theorem, so you have a total elastic amplitude, and then you're taking the real or imaginary part depending on where you put your eyes. So to get the total cross section. So okay, so where do you get this elastic amplitude? We want to do light cone perturbation theory. So what we do is that we take the elastic amplitude by taking the expectation value in a photon state. So this is the incoming photon state, and we're taking the expectation value of the scattering T matrix element in this scattering T matrix element, or the S matrix minus 1, with in the photon state.
Why is it a photon? It's a photon on the target state.
Yeah, so I'm not writing. So somehow the target is here. The photon, it's an incoming photon. It's not a.
Okay, I know what you mean.
Yeah. So the target is here. Okay. This is scattering from an external potential. So in some sense, there's no this.
He knows he's just trying to delay.
Yeah. Okay. you know this perfectly well. You wrote the book on this, so it's.
I didn't know that.
Okay. So here, we're working with the high energy limit. So this S is iconal scattering, which translates into Wilson lines. The amplitudes can be given by Wilson lines in coordinate space. So if you want to do NLO, what we want is that we want the Fock state decomposition of this virtual photon state up to coupling G squared. And what are the terms that appear there? So this is the full interacting photon state. There's some renormalization coefficient. Then there's a bare non-interacting photon state. That's not interesting for QCD. The interesting things for QCD are the QQ bar state. This is the dipole, and the QQ bar gluon state. At this order in perturbation theory, we have these two possible Fock states in the photon wave function the photon state that we are interested in. And at this order in perturbation theory, okay, and and the coefficients of these Fock states are what are referred to as light cone wave functions. So this is somehow the definition of what a light cone wave function is. The interacting theory state, written as a linear superposition of non-interacting states, their states, has some coefficients, and these coefficients are what is known as light cone wave function. So we need light cone wave functions gamma star to QQ bar and gamma star to QQ bar G up to order G squared. Okay, so how does one calculate this? And there's a well-established perturbation theory for how to do this. And so we have this light cone perturbation theory diagram to calculate this. What we need at this order is the gamma star to QQ bar wave function to one loop order, and the gamma star to QQ bar G at 3 level. So we calculate these from the diagrams. Then you Fourier transform, and this is what we rewrote the book on. Right? No, like on LCPT. Then you Fourier transform to transverse coordinate space because this is where we know how our target interacts. We do have this iconal scattering amplitude, so we need to go from transverse momentum, which is the diagrams are in transverse momentum, so we need to Fourier transform, go to transverse coordinate, because it's in coordinate space that we know how the target interacts with the photon. And so then you need to square, because what you're calculating is this kind of an amplitude which has the same photon state here and here. So basically you end up getting squares of these two wave functions. That's what the cross section is. I'm not gonna somehow write all the LCPT rules here, just try to highlight some things that I will come back to in the case of masses. So for massless quark, so somehow this is the basic vertex, and then you have all the different combinations, a quark emitting a gluon. So there's a couple of things that most of you already know very well. What one But one does in these LCPT states, LCPT rules, you have energy denominators, and energy in Litecoin is K minus. So those are differences in K minus between the initial state and then intermediate states. And here, since this is a Litecoin wave function, this state at the end is also an intermediate state, because this is something that then goes on to scatter with the target. So this is not an outgoing state that actually comes out of the process, but this is also an intermediate state. So it also has an energy denominator. The K minus difference in K minus between this state and this state. And then on shell vertices, the interactions, and most importantly, one has the QQ bar G, or quark, or let's say fermion gauge boson vertex. And these are evaluated with on-shell spinors, but with K minus not being conserved. So free momentum is conserved, but Litecoin energy is not conserved. And what I prefer to do is to write this matrix element in this kind of a form. So there's a momentum fraction, which is the fraction of the plus momentum taken by the emitter, taken by the gluon. And there are two different Lorentz structures. If I separate out, so this is the transverse polarization vector, because one just extract the transverse component, work in terms of the two-dimensional components. So there's a transverse polarization vector, which has a vector index, a two-dimensional index. Then there's the kind of the center of mass momentum of the splitting. This is somehow the natural momentum that this splitting vertex depends on. So the matrix element is given by these two-dimensional vectors. So there are two possible in this for the massless case, you have two possible Lorentz structures, two possible index structures here. One is a delta ij, and one is an epsilon ij. So one can write the whole vertex in terms of these two structures. And in both of these, helicity is conserved. So for massless quarks, there's no the helicity of the quark before and after scattering is the same. And then you have some coefficients. H here is, in my conventions, H is plus or minus 1.
Let me ask a technical question. When I'm calculating imaginary part, which is the same as your calculation, this P prime is on the mass shell because imaginary part.
Yes.
P is not on the mass shell. Why you are?
So here P is also on the mass shell.
But then how you will recover impact factor?
But by integrating the impact factor over K minus. So this icon perturbation theory, to obtain it from covariant perturbation theory, you're putting everything on the mass shell, integrating over K minuses, and then integrating over Litecoin time, which gives you the Litecoin denominators. So this here is not exactly a piece you would recover in covariant perturbation theory. It's just by putting those together, that all the integrated pieces.
And so when you take an imaginary part, you have those energy denominators, which means sort of your intermediate state is not on energy shell, your energy is on but the imaginary part puts it back on energy shell. So imaginary part in the standard perturbation theory puts particles on mass shell, in Litecoin perturbation theory it puts intermediate states on energy shell. I think in fact actually that's how you prove Kapkowski rules by going to time order perturbation theory and doing this energy shell.
Is it technically more convenient that just calculate imaginary part?
I would argue this is much less convenient.
Well, then we can do
I think it's a matter of taste. And
It's a matter of taste. There are questions of what is convenient calculationally, and then there's also what is somehow gives you a more physical picture of what is happening. Somehow, in some sense, the thing with the Litecoin perturbation theory is that you lose some of the calculational convenience, but you gain a more physical picture of what is happening. Okay, so the way I'm writing this as epsilon ij is actually too simple. That's fine when working in d equals 4, but actually, of course, you want to work in less than 4 dimensions to do dimensional regularization, and in less than 4 dimensions, delta ij is perfectly fine, but you somehow need to write this essentially. Well, you need to write this in a way that I will have later on in my slides. So the important point is that there are 2 index structures, and both of them are helicity conserving. Okay. So what happens then? So you calculate the loops. So there are virtual corrections, which are one loop corrections to the gamma star to QQ bar Lightcone wave function. So there's a couple of loop integrals that you calculate. Then you Fourier transform, and then the way this kind of a dipole state interacts with the target is with this dipole amplitude between, or quark anti-quark dipole amplitude. Then you have real corrections. These are you work at tree level because the loops in here would be too high order. So the interaction with the target involves some other amplitude for quark anti-quark and gluon state to interact with the target. Okay. So then you have some divergences. These are loop divergences which have UV loop integrals which have UV divergences. So you do this integrals in momentum space in dimensional regularization, and you have 1 over epsilon UV divergence poles, which are there. So there's a UV divergence from the loop. Here, at the level of the Lightcone wave function, this is just a tree-level diagram, so there's no divergence. But what happens when you actually calculate the cross-section? You're squaring this, and you're integrating over all the intermediate states. In particular, you're integrating over the coordinate of this gluon. And there's a UV divergence in the integral over this x2. Basically, when this x2 becomes close to x1, there's a UV divergence in the square. And these UV divergences have to cancel between each other. And what guarantees that they do is that these amplitudes for these states to scatter with the target have to satisfy a certain condition. They have to satisfy the condition that when you take x2 going to x1 here, for x2 going to x0, then you recover the dipole amplitude. So when you take the coordinate limit, when this coordinate becomes this, then this becomes this. Okay, so the target, the amplitude. Otherwise, at this point, I wouldn't even need to talk about Wilson lines. I would just say that my target is described by scattering amplitudes. I describe what my target is by telling how a quark anti-quark dipole scatters over the target. But if this is completely general, I don't. Then one would separately need to impose this condition. Of course, when I have a picture of my target as in terms of Wilson lines and color fields, then this is automatic because that just follows from the definitions of these guys in terms of Wilson lines.
It really follows because you have color neutrality.
Exactly. Yeah. And this is some of the color neutrality is built into these Wilson lines. Okay, so you do the calculation. I'm not gonna even write the formulas here. You can do them. So, in order to evaluate the cross section, we write it in 3 parts. Okay. So there's the leading order. So there's a leading order cross section, which is just the leading order wave function squared times the dipole cross section. Then there's a lot of asterisks here. So what you have at NLO, you can split the NLO corrections into two kinds of contributions. Now this is the NLO kind of in some sense what comes from the loop diagrams. So from the virtual corrections minus the UV divergence. Okay, so I have to took away the 1 over epsilon part, and what remains after this subtraction can be written as just something which is alpha s, the leading order contribution times this log and pi squared and so on. So there's just a simple function there. This part is very nice. Okay, and then what remains from the quark gluon contribution, so from the real contributions, plus adding here the UV divergence that was subtracted from here. So this correspondence, this diagram doesn't exactly correspond to this expression because I added and subtracted the UV divergence part. But apart from that, adding and subtracting the UV divergent part, what I have is the wave function gamma star to QQ bar G wave function squared times the amplitude for QQ bar G state to scatter from the target. And then here in addition to this UV divergence cancellation, what I have to do is that I have to subtract the leading log, which is already in the. I have to subtract the leading log, which was already included in the leading order contribution, which has a decay evolved. Which has a decay evolved.
Or I need UV divergence. Electromagnetic current It's not normalized. What UV divergence?
So the final result does not have a UV divergence. The way it comes across in this, like in this calculation, is that there are UV divergences in the loop and in the real correction, and these cancel each other.
And there is
So
no
physical.
self-energy in this approach. There is no self-energy diagram.
They are. I mean, I'm not drawing all the diagrams. So the self-energy diagrams are part of this. That's also loop correction, and so this is.
But
It goes in
I
here.
guess his
I didn't draw
UV divergences do not cancel the integral between virtual term and
No, so the total one loop gamma star QQ bar wave function has a UV divergence. Even if you add all the even after you add up all the diagrams, for gamma star.
all the
QQ bar.
diagrams means you have to add the self-energy.
Yes. Yes.
And they don't. Z1 equals Z2 doesn't.
No, that's current value. No, but the main reason why it sounds confusing is that this is completely massless. You don't have to renormalize the external lines. So all the dot poles are set to 0. Which means that infrared and UV.
No, but these are not external lines. So
No,
they do
No,
have.
I agree. But the real correction you would expect to have soft dimensions. Like infrared, not UV.
Yeah.
And the point is, in this case, UV and infrared are the same because it's all massless. You don't have to renormalize anything. Just set the type of 0.
UV and So in some sense, what you're used to thinking of as a UV divergence, in some sense, here appears as what you're used to thinking of physically as an infrared divergence, somehow the cancellation between real and virtual. Here in this calculation, it appears as a UV.
Yeah, I mean, you would cancel the UV from the virtual term with the UV part of the dipole and the infrared of the real term with the UV part, the infrared term of the dipole. But since you set the dipole to 0 as 1 over UV minus 1 over infrared, it doesn't matter. You can just cancel each other.
So which dipoles?
Well, like
1 over k squared there.
yeah, I mean, okay, in this case, okay, this is completely inclusive, so I'm not completely sure. In my case, for diagrams, you have renormalization of the external lines, and those diagrams are dipoles.
So basically, somehow what you have is so what you have is so somehow this cancellation is basically what you have already in the BK equation when you decompose the BK kernel like this, so that you have x minus 2, x minus z, y minus z over x minus z squared, y minus z squared. So there's a cancellation. There's a cancellation between these two terms, and so there's a divergence when z goes to x, which cancels. And this is that's a UV divergence. It's a short distance divergence.
It doesn't cancel with the lost terms, by the way. It cancels by
Then the other.
n terms. No, the n terms multiplying. It doesn't cancel on the term.
Again, they find
Often they deliver with some money.
You see that second term isn't infrared, isn't singular as x goes to z, aren't they? Iterable.
That's right.
So it's the rest of the expression.
Yeah. So forget that. Yeah.
No, but I mean, but this is a small x example, right? We're talking about UV divergence. So your U1 is not the soft U1, right? So we're really just, I mean, Jan's question, I think you have in line 2, you have a vertex correction and 2 so-called self-energies, and you're saying the UV divergences don't cancel?
No.
See, if your external lines, if you're putting square roots of z2 on the external lines, then they should cancel.
Yeah.
If you're putting square roots, and so it's a little bit depends on how you do your counting.
Yeah, but here you don't have, because they're not treated as external lines.
Yeah. If you don't put square roots on the z2s, then they won't cancel.
Well, I guess in a way, yeah, if you write it in a factorized form as a wave function, dipole amplitude wave function, then you can kind of like do the bookkeeping in such a way that the corrections, virtual self-energy corrections to the wave functions will generate one factor of square root of z2. And then you on the incoming lines in the dipole amplitude, you also have to virtual corrections with another square root.
Yes.
Then Jan would be happy, your wave function would be perfectly fine, and then you move your program into the that's what you mean.
Yes.
Kind of treat it like a quasi-external line.
Yeah. So you could, I mean, with this kind of, you could chuckle it around, but in the conventions, what I use is that somehow these are not, this has a UV divergence, and then the target has no square root z's, it's just the Wilson line.
But that answers the
Just for the identity.
Yeah, the fact that square roots of Z2 and Z1 from the vertex cancel, that just Z1 equals Z2,
Eventually, all you do the random cancel.
Yeah, so okay, so the UV divergence, the 1 over epsilon UV divergence cancels. Then there's this leading log of x or k plus, which then you have to absorb into a BK evolution of the target. So that's it. Okay, so there's this leading log, so you need to subtract it. So there's a lot of indices here. The important one is that I denote Z2 as by Z2 the momentum fraction of the B1. So I'm, of course, in the full expression, I'm integrating over Z2, and this integral is divergent in the limit Z2 going to 0. So what I do is that I subtract the same thing with Z2 replaced by 0, and this is subtracting the leading log, which is already there in the fact that the leading log contribution has a BK evolved cross section. So okay. So here, parametrically, now these target scattering amplitudes are evaluated at some scale capital X. So this is the capital XG of in Edmond's talk, which in general depends on Z2. Okay, and here
being fractional.
Z2. So Z2 again is the momentum fraction carried by this U1.
confused with the Dionysus. Dionysus is notation. This is transverse coordinates.
So okay, so in this respect, and so what happens here is exactly what Edmond was describing in his talk. In the case of single inclusive, the issue here is completely the same. So this term is like the CF term for Edmond. This term is the NC term. Is somehow the analog of the NC term in Edmond's talk. And so this term is what is associated with the BK evolution of the target. So you have some wave function, which is somehow the kernel, and then you have the scattering amplitude, which has to be evaluated at some rapidity scale. So when
why it's strange, because when you do factorization, your rapidity scale is always the same. That's
yeah. So this is exactly. So we just had this discussion at the end of the previous talk. So it's exactly the same. So the physics is exactly the same. So parametrically, you would say, and this would be KT factorization, that this x, that this capital X, you just take it to be x, b, or k. Then you have KT. It's not KT. It's not the same coordinate space. But then you have factorization in the sense of KT factorization. So you evaluate the target, whatever the target is, you evaluate it at the scale of x, b, or k. But exactly as Edmond was describing, what happens here is exactly the same as in the single inclusive case. In order to get a sensible result from these formulas, it's essential to have this rapidity target scale depending on the Z2 which you're integrating on. So not just evaluating it at x, b, or k, but evaluating it at a scale that depends on the momentum of the group.
At this point, you are starting to model an NLO, yes?
Yes. Not just NLO, probably a higher order.
Okay. So, okay, so this is, and okay, so the expression for this is more complicated. You can find it in the papers. It doesn't help us anything to write it down. So let's just see what happens when you put this when you evaluate this. Okay. Okay. So I'm just somehow this is just recalling what was here. So somehow in a notation that is similar to what Edmond was using. So you have the full NLO result, and then you're subtracting the BK, and then the question is, at what scale do you evaluate the target fields and the target the dipole cross section? So this plot is taking this kind of the KT factorization in the KT factorization way, where you evaluate it at the scale of x, p, or k. So this is what would correspond to KT factorization. So here, this bot is not necessarily the easiest to read. Note that the 0 is here. So the blue line is leading order. And then there's two kinds of NLO corrections. The green one is what I call the dipole correction. So the green one is this. So this is the thing that's not associated with decay evolution. It's just a separate term, like the CF term. So if you add the leading order plus that term, so okay, then there's a positive contribution. It changes the cross section a little bit, but that's not particularly problematic. The red one is the leading order plus this QG contribution. So plus the contribution that's associated with the decay evolution, where you evaluate these at the scale XBRK, and what you see is that this red line, it becomes negative. So somehow this correction, what you're subtracting is bigger than the thing that you're subtracting it from. So this correction written like this. So the NLO corrects, this part of the NLO correction is negative. It's larger than the leading order cross section, and this is a discrepancy that grows when you go to larger Q squared. So this is the analog of you run into for single inclusive, you run into problems at large PT, large KT of the produced particle. Here, a similar thing happens when you go to large Q squared.
But it's quite large Q squared here. It looks like before you. Right. So if I read this right, you only have 15% correction at Q squared equals 100.
Well, okay. So these are very close to zero. So it's so there are. Yeah. So let's. It's better to in the following. Later I will have NLO leading order. So it's easier to see what the there. But this is.
Does the whole thing become negative?
So the whole thing. This is the whole thing. This is the full leading order plus NLO. So that also becomes negative. And so this is the whole thing. So this is the leading order. This is leading order plus some of the NLO. That's not the OK part of the leading order. This is NLO. This is leading order plus the problematic part of NLO, and this is the full NLO. So somehow having this four curve just illustrates that the full cross section does become negative, and the reason it becomes negative is because of this part of the NLO correction. The other part of the NLO correction is perfectly fine.
At what point you integrate your impact factor with decay evolution?
Here. So this is the impact factor,
yes.
And this is the BK evolution. So this is a BK evolved. So this is a BK evolved dipole cross section evaluated at some scale XBRK.
And numerical integration.
Yes. Yeah. There's a numerical integration over lots of variables.
And N012 is taken in much and CV?
Yes.
Or you actually do some fields?
You do the field. Well, the coefficient, this N02 actually turns out being NC over CF times the BK operator. So this actually changes into NC even at finite NC after you do the field thing. But then it's then you have to factorize. So it's in what I would call the mean field, what you call the large NC, what I would call the mean field limit, where just the dipole squared is taken as dipole times dipole.
And if you do
the
just
same as
BFL, you have problems. I mean, if you do just BFL, multiply it by the second dipole which you calculated, get cross section, will it also be negative?
He's saying
I would assume that the C would have the same problem with the FKL. I haven't seriously thought about that. I think if Edmond's interpretation of this the origin of this negativity is correct, then I guess you would say that you would get the same thing with the FKL.
Just if I like to even yes, told that they get negative cross section in NLO. For them, it's a part what they call a skin defender, but they never heard the family use that.
Yeah. So this I have to say with credit to after we had done this, and then we were pointed out by Guillaume that in Guillaume's paper from 2014, I think, on the kinematical constraint, what he does is that he goes to the dilute kind of the BFK limit from BFK limit of these. Then he goes to Mellin space. So he works out what you get in Mellin space with the two prescriptions with this prescription and with this one. So this is the analog of CXY. And somehow what he claims, he looks at the Mellin space expressions, and the claim is that you also somehow
See the problem.
Yeah, but you see the problem from there. I don't recall the detail because I don't have an intuition in knowledge space.
Yesterday, Dionysus was telling us that you need to put scale, transport scale to eliminate the negativity problem. And here you put longitudinal scale. So it's a different problem.
Sorry, I missed it.
Dionysus
It's a different
yesterday was
problem.
telling us that
Yesterday was about the standard law. Here's something that is rapid subtraction. He's a locality approximation in rapidity. In that case, where genuine large periodic operations enhanced by parallel laws. So I don't see the connection.
Wait, so you're saying that
no,
Dionysus,
but I can try the relative size as the improvement, not transfer size, not longitudinal fraction.
It's actually disconnected.
Yeah, I don't see any connection. In that case,
This is more a convolution with impact factor. This is not.
The idea was that in general, idea was that as S divided by Q square, always, yes. Then you can improve your Q square or improve your S. In this case, you are improving your S in a sense. But yesterday, they were improving Q square. Well, maybe not. What is not clear?
no,
You have leading laws. They are always S divided by some Q square, yes.
that's about impact factors, not about the evolution.
It doesn't matter.
So I think that's
They
probably
don't
also a
know.
question of
They
Q
don't
square.
Yeah.
Then it's probably also a question of Q square. Log S we all agree on, right? The uncertainty is always a Q square. So then we should go to Dionysus, ask him for his answer, come here back and fix all the problems.
Oh, good luck. They're not related, right? What Dionysus talked about has nothing to do with this. What Dionysus talked about yesterday doesn't have anything to do with this.
Yeah, that was a different. What Dionysus was talking about was
Well, what
that
Edmund
was higher
saying-
order.
No, what Edmund talked about this morning has a lot to do with.
Yeah,
what
but
he's
this is
talking
the same as Edmund, this is exactly the same issue as Edmund was talking about this morning. Not the same,
But
not the same thing
wasn't
that
Edmund
Dionysus
talking about putting the correct argument, the correct X
Yes.
in the argument. Isn't it the
In the
same
impact
thing as
factor.
running?
All the
No,
time.
no.
What Dionysus was talking about yesterday was the evolution. What we are talking about, Edmund was talking about, what I'm talking about is the impact factor.
Your idea is all this
And this is the,
okay. You will avoid negativity if you cleverly assign arguments as you are.
It's not the
Yeah,
input
but that's not
factor.
going
Edmund
to,
was talking
that's
about.
not going to avoid what Dionysus was talking
Which is not to avoid this.
about. If you choose the proper
Yeah.
scale, that's
No,
not going
that-
to change what Dionysus.
Okay, so can
It's still
somebody
going to-
explain to me? So Edmund was not talking about impact factor. He was talking
Well,
about.
Yeah,
that-
he was
he was talking about
he
impact factor.
was.
Yes, but the amplitude, the calculation of the NLO impact.
Yeah, but the amplitude, it comes at the number, but
But this is not about the impact factor, this is about the convolution. So where,
It's about the
what
convolution.
probability you're convoluting your exact factor with the solution?
Exactly.
So where do you evaluate them? So it's linked.
That's simple.
it's linked, but it's linked, but here we're not
If you're
talking about.
factorizing, it should be independent. What they are saying now is that maybe it doesn't factorize.
I mean, the issue in Edmund's talking here both is trying to do a subtraction to factorize a small x
he was
evolution.
trying not to do it.
But look,
We would all
somebody
like
has
to do factorization, but both Edmund and
that-
I are showing that it just
That's the
doesn't work.
subtraction.
He does not, and he does. He got the problem.
No,
Okay, so so should we-
Dionysus wasn't factorizing the small x. He was talking about the evaluation of the kernel, which you use
But
evolution.
at higher order,
Let's say-
because this is leading order evolution.
I mean, here it's this game, whether
If it's leading order, X will be the same.
I mean, the NLO impact factor gives you leading order evolution equation.
Yeah, it's NLO, yes.
Yeah, but Dionysus was talking about first. It was a separate problem.
I mean,
You see, what the- he
Yes.
said nothing to do with it.
So should we go on?
Yes.
Okay. So let me go on. So that was the plot. That was the plot for kind of, this is the analog of CXY for the single inclusive. This is the more or less the analog of what Emma was discussing. Emma's procedure was single inclusive. So if I take the scale here at which I evaluate the dipole cross section of the target, just as x Bjorken over Z2, I get results which are reasonable. So here's the leading order is the blue. So leading order plus the non-problematic part of the NLO correction. That one part of the NLO correction makes it is positive. It makes it larger. Then there's another part of the NLO correction which is not which doesn't make the cross section negative anymore. It's more benign. It's still large. So you get the subtraction, and the total NLO after this. So you have a large positive contribution, large negative. The total NLO is very close to the leading order. Very close to the leading order result with this change.
So you didn't have to do this.
Exactly.
I think so. This with this.
No, he did that what I did.
Okay.
No,
No, you should have been.
Okay, so
happily ever after was
You're
it's a bigger receptor
suggesting a
NLO.
scheme where higher order corrections are zero, so you don't have to do anything.
Exactly. But the fact that they're so close to zero is basically an accident. It's basically somehow accidental
There are
here.
no accidents.
Yeah, for FL already the correction is bigger but somehow the point is that if the NLO corrections are small, it comes from a large cancellation between physically very different kinds of NLO corrections with different signs. Okay. And that's actually the same for single inclusive. Actually, also there the CF and the NC have different signs. So if neither of two blows up, they cancel each other to a large extent. Okay. So here there are some technical details. When you integrate over Z2, this is the lower limit issue. So here we also when you have a Z2 dependence here, you cannot set the lower limit to 0. So you cannot integrate from 0 to 1. You have to integrate from some finite limit to 1, because otherwise this would not make sense. So what we do here is that we take this. This is the limit we put, the lower limit, which is kind of estimated from the target, from the K minus, assuming that the typical KT squared here is of order Q squared, and this is not really correct. Somehow the it's a KT meaning the KT of this gluon. The KT of this gluon is really it's integrated over a broad range, and basically receives integrated from some softer scale up to Q squared. So this is, we know that this is not correct. It's just somehow, this leads to something which is very simple to put in the formula and calculate. We know that this is not really the correct, this is not really the correct estimate for the lower limit of Z2. And so this is one of the things that one has to think about more. If we would really do the factorization like Guillaume does in strictly, not in K minus, but K plus, somehow there you can set the limit. You would know that the limit, Z2 limit, should go like X0 or X0 times some one proton mass scale over Q squared. So the limit, Z2 limit, should be smaller. But then on the other hand, so you would add something, you would have a larger integration range here, so you would add something to the cross section. But physically we know that should be compensated by having, so you would have more in the cross section. That should be compensating by having less evolution, because physically you should have this kinematical constraint which would slow down the evolution. So there should be physically, but somehow there will be a compensation between these two effects. It's not obvious somehow how this in the end works out. So what we're doing here is a simplification.
Sorry, just to make sure I understand it. So your X, capital X, now is X Birken over Z2, and Z2 is of course smaller than 1. So you really are evaluating the dipole amplitude at X smaller than X Birken.
No, larger. So Z larger than X Birken. Z2 is smaller. So that's the point. So when you integrate over Z2, you're integrating on the evolution, BK evolution history from the initial condition down to X Birken, and because you're integrating the whole history, somehow the history of the evolution down to the initial condition, then it starts mattering what you put here as the limit to you. What is the X0 where you start?
No, I understand. If it goes to 0, your effective Birken X goes to infinity. That's not a good thing.
Yes.
So obviously.
And so this is one of the problems in this non-factorized form. It will be nice to have the cross-section just at X Birken, because then you don't need to care about what the dipole cross-section is at X equals X of order 1. But now when you do this, you're taking the dipole cross-section from the whole evolution history And then for a practical calculation, you need to assume something about it at large x. And that's annoying.
Not even the right degree of
That's
freedom.
Yes, so that's annoying, and that's somehow, and this is...
Question. Is NLO, I mean, there was NLO plus some guesses. NLO result correct? Or because, well, when we were factorizing, we just factorized the integral in Sudoku variables and K plus in and we were careful to match impact factor to the evolution. Yes, miss nothing. Here you were changing something. So did you check that you didn't miss anything?
Somehow, the fact that this matches perfectly with leading order BK evolution.
Leading order, no.
And of course, an NLO, and so then the NLO BK that requires actually calculating the impact factor at NLO before you see precisely how you match with NLO BK. And those are diagrams that, I mean, these are the diagrams that when you derive your NLO BK equation, you calculate these diagrams in the limit when the gluon is soft. And nobody has calculated those diagrams in the limit when the gluon has arbitrary limit.
We did simply nothing. We took, took Feynman diagram, rewrote it as integral transverse momentum and rapidity, whatever take, cut in rapidity, assign this to impact factor, this to evolution, but the match was exact. And here you say that, okay, one photon goes into quark anti-quark. You assign one cutoff to the quark, another cutoff to anti-quark.
What do you mean? I don't understand what you're saying.
Okay,
so this procedure. So this is the thing. So this is exactly as in Edmond's talk. This procedure, when you write it like this is exact. Okay. This is exact.
Computer's diagram, right?
This is so you're just computing these diagrams, making no approximation.
When you put n of x of z2, you are doing something. And I am asking, does this something reproduce NLO result? So leading on of course, NLO.
No, there's no way you can. So you mean NLO BK? There's no way you can. You cannot reproduce NLO BK from this calculation. Because that would be NLO BK. The diagrams you have in NLO BK are higher order in alpha S, alpha square diagram. This is only alpha S. You cannot because that NLO BK is higher order. You cannot reproduce it.
Matches with leading order correction BK or the graph.
Do you mean that on the level of NLO BK, I can put any x for upper quark or lower quark and still get correct result, NLO result? Is it right?
What has to do with NLO BK?
I think what he's
No,
saying
NLO
is
BK, whatever.
No, there's no higher order. It's not done at that level.
Yeah, I mean,
You're doing a much more ambitious.
Let me go back to
thinking much more ambitiously than Thomas is calculating.
This is basically what I was saying here. So somehow, what you do in NLO BK, you're calculating diagrams of this order, and and if you so somehow this is an NLO BK is calculating diagrams of this order and extracting the alpha. So these are alpha squared diagrams, and you extract the log 1 over x part of these, and this is what gives you the NLO BK curve. But these are diagrams that we. Yeah, so these are diagrams from the NLO impact factor, which match to NLO BK. But here, what we are doing is that we are doing this. We are looking at this. We are looking at the NLO impact factor, which gives you leading order BK.
But can I clarify? I think what Jan is asking, that your choice of the x in the argument of n is effectively an NLO correction.
No.
If you're telling us a particular choice,
yeah,
should map your NLO
exactly. So just like
if it doesn't, then
just like in Edmond's talk, I think there is the difference is formally in the higher order. Yes.
higher than what you calculating, but it's of the order of the.
But I think it's. I don't think it's. No, but it's higher order, but it's. I don't think it's NLO BK. It's of the order of NLO impact factor.
You should calculate.
But impact factor should have the same form, right?
Look, it's like diplomatic scattering. You have two loop anomalous dimension, you mesh to one loop coefficient function.
Exactly.
Same
This is
thing
the same thing here. So this is NLO impact factor, which matches to leading order evolution.
But it was vice versa. Impact factor is coefficient function. So it's not, it's vice versa.
So like it's a D-lab. You calculate, start calculating NLO cross sections. You extract the log, and this is leading order evolution. So it's always the NLO cross section gives leading order evolution. NNLO cross section gives NLO evolution, and so on. Okay, let me go on. So there's tricky issues about what exactly the limit here should be, and then what you do in practice, and so on. And so then for the other non-problematic dipole term, what we do is we just integrate from down to 0, because that's an integral, that's a finite integral you can do. But here you cannot, for this term, you cannot integrate down to 0, and there's somehow there are issues about what one should do here. Okay, so general features, there's a major cancellation between different kinds of NLO terms. So this is the leading order, full NLO, all NLO terms. For FL, it's similar, although the cancellation is not as exact. So this is leading order, this is NLO. So somehow for the for FL, there's a positive term and a negative term, but they don't cancel as well. So the difference between leading order and NLO is bigger. So now the way this is implemented now, so this comes back to this lower limit issue. What we do is that we take this lower limit to be x Bjerkane or x0, which basically means that we're cutting off all the phase space from large x, so we don't need to evaluate the dipole cross-section at all at x larger than x0. We're not assuming anything, we're just setting it to 0. But what this means in practice is that this implementation explicitly sets the QG, this somehow the problematic term, NLO correction to 0 at x Bjerkane equals x0. But then there's a cancellation between the two kinds of NLO terms. The other NLO term in this implementation is not set to 0. So this means that this cancellation stops working when you're close to the initial rapidity scale x0. So you have this large transient effect, so that here the relative NLO correction is very large, close to x0, because one is taking a different integration limit for the two kinds of terms, which somehow naturally would want to cancel each other to a large extent. Okay.
So x0 is 10 to the negative 2.
Yeah, x0 is 10 to the minus 3. And then we also, so those were all for fixed coupling. Now this is a parent dipole running coupling, and the transient effect is even larger for some reason that I don't fully understand why. So what is here is FNLO divided by leading order at L longitudinal and transfers at different Q-squared values. And when you go to x Bjerkane close to the initial x0, there's the leading order NLO over leading order ratio gets somehow, depends a little bit, but can get very large. And this is really somehow this transient effect from the two kinds of NLO corrections would like to cancel each other to a large extent, but in this particular implementation they don't. And certainly this is somehow not the final word there. Now the Q-square dependence is relatively stable. So of course there are differences between different kinds of running or fixed coupling, and there's differences between longitudinal and transfers, but there's nothing dramatic happening as a function of Q-squared. So the overall conclusion is that the NLO corrections are, the relative value are somehow of the expected, they are alpha is corrections, 20, 30, 40% corrections. But in order to actually fit data, one needs to think more carefully about how to treat the limits, how to treat the different kinds of NLO contributions in a consistent way. So there's still somehow more of this kind of work to do before one can really start comparing the data. Okay, so that was that. Let me say a few words about massive quarks. So this is something that we're currently working on. So why do we do massive quarks? There is data from HERA. There will be data from EIC, inclusive and exclusive data. So you certainly want to calculate massive quarks. It's a dirty little secret in this business that heavy quarks with RCBK fits do not actually work all that well. And this is not really advertised.
I thought F2 charm works for CBK reason.
No, it works by cheating. Just full out cheating. So this is, you mean AAMQS?
I thought so, yeah.
Yeah.
But,
So AAMQS quote a very good chi-squared. How do they do that? They have a separate sigma 0 for the proton, for the charm heavy quarks. And so what they achieve a good chi-squared by saying that the when measured by charm quarks, the proton is half as small as measured by light quarks. So basically, this is completely disagree. Yeah. So the only way they fit F2C and F2 in the same fit is by really saying that the charm quarks measure a different proton. The charm quarks measure a different target than the light quarks. Yeah. So this is here. Okay. So with my fit in Heikki's fit, we only use light quarks. We have tried to somehow just extend this to heavy quarks. It doesn't work out of the box. Somehow it doesn't like to work. Edmond's and so Gregory's and Edmond's fit is actually better. So somehow this collinearism fit does improve the problem, but also Gregory only gets a good chi-squared by using old Hera data that has large errors. So the new combined Hera heavy quark data has smaller errors, and Heikki and Gregory have looked at that, and this is unpublished, but they have looked at that, and the fit gives the chi-squared is not that good when you take the more precise data. So this is the best so far in some sense, but it's still not satisfactory.
Is it clear that the lifetime of the dipole is not enough for heavy flavors for this dipole picture to even be valid?
Well, I mean, the
charm
charm
should tell you.
no, but no, that it's still at small x, right? That shows up in the at x. If the quark is heavy enough, you're not at small x anymore, and then of course you don't trust the dipole picture. But still, if the energy is high enough so that you're at small x,
The lifetime is related directly to the log of 1 over x. And so as long as you start at x0, as long as you start at x0 small enough, you always have a big enough lifetime, independent of the mass.
Yeah. So the lifetime really is something like
the lifetime
plus momentum over z1 minus zq squared plus m squared.
And it all breaks down to a logarithm of the 1 over the Bjorkane x times some property of the target, some mass in the target.
Yeah. So exactly as you Yuri, exactly as you say, it's the energy divided by z1 minus zq squared plus m squared. But now basically m squared is of order q squared or less. I mean charm quark mass is 1 GeV.
Right, but your energy
it's
also depends on z, and if you have a line jet configuration dominating the z factor in the numerator also.
Well, but the line jet configurations are, line jet configurations then are a problem also for light quarks. So that's.
No, I mean the z goes to 0 in the denominator in the heavy quark case. You would have one.
Or are you now saying that the dipole picture is only valid for line jet configurations?
I'm saying if you're looking at F2, right? That's trouble, maybe.
Yeah, so that is the trouble. So okay, but
okay. Anyway,
somehow in some sense the aligned jet configuration is why IPSat is the only model that really manages to get charm and heavy quark and light quark data, but that's not BK evolution. So it's somehow they achieve this in a tricky way. So it's somehow amazing that it works.
The X dependence there is put in by hand.
X dependence is put in, so this is why it's not on this list. That's why it's not BK. It's not BK evolution. So there's a recent work by Heikki and Björn where they look at impact parameter dependent gym walk. So B dependent is essential here because that somehow forces you to actually take a stand of what the target looks like and what the transverse extent of the target is. And also what they also see is that they don't achieve a description of F2 and F2C simultaneously with the same parameters. In the same way as AA and QS also doesn't describe them with the same parameters, they have a different sigma 0 for lifetime report.
Should you consider some background correction? Because you have massive work, and massive problems travel on the straight line and so on. So you have to take the issue.
Do you mean they don't travel on the same?
But not that massive.
No, not that massive.
Sharp works, not top works.
You don't mean that. It's F extra F divided by mass of the quark. F, I mean, it's fluent.
In the high energy limit, massive quarks have travel on iconal trajectories just as massless quarks. As long as you're in the high, as long as the energy is large enough.
And the approximation is higher.
It's higher, yeah. But that's the same question Yuri was asking. If the lifetime is much longer than your target, then they'll travel along straight line trajectory. If it's the order of the target, so then they'll be curvature, right? That's the same question Yuri was.
Extra insertion means fluent field. Yes, it's a order of mass of the hadron divided by mass of the heavy quark. It's correct.
For charm core, the mass of the hadron, mass of the charm core is comparable.
Because,
If that's
because it's in your target. Your target is hadron. No?
Yeah, so
I'm not sure that's a figure of merit. That's all right.
Okay, well, you get, you take, you expand, make a direct expansion of two currents with charged quarks, yes? Then, result of this expansion, there are some Wilson line, maybe some F menus running around with Wilson line in subiconal. And then you evaluate it between hadrons. And each F menu can bring only mass of the hadron. It cannot bring mass of the charged quark. So, I think.
So what's your statement?
Statement is that, yeah, it's iconal. You don't need to go to calculate this, you don't need subiconal current.
okay, so in addition to that, doing loops in LTPT with massive quarks is also fun, especially when it's Risto and doing it and not me in the actual loops. So there are new Lorentz structures which give new somehow Lorentz invariance constraints. So somehow the mass renormalization is actually problematic, and this has been known in the field for a long time. So the approach that I will follow in this talk first is that I will start with the same regularization that we were using for massless quarks. So you just put a cutoff in K+ integrals and do just a normal transverse dimensional regularization in transverse momentum. So let's start with this. Okay. So what changes when you have a quark mass? In addition to the two non-helicity conserving structures, so this is the generalization, this is the epsilon ij. When you write it in this way, you can generalize this to arbitrary dimensions. So if you do dimensional regularization, this you have to write it like this. With the massive quark, there's an additional term, which is a spin flip term. Guillaume tells me I should call it a light cone helicities flip. I will call it a spin flip. It's a shorter word. Anyway, I'll call it a spin flip. It's a shorter word. Spin is a, but I know, I mean, this is, I'm sloppy. Fine. Maybe I should just call it flip. And so the additional term is a flip term, which is proportional to the mass. And then it has a different Lorentz structure which vanishes for massless quarks. And the other thing to note is that there's no transverse momentum. These are proportional to the transverse momentum. This is proportional to the mass instead, so that affects the power counting of what actually diverges. Okay, so let's look at what are the new UV divergent and what kind of new UV divergent and what kind of new finite contributions we get from this additional structure. There's two things one needs to look at: the vertex correction diagrams, where the calculation is a bit more complicated, but the physics is conceptually simpler actually. And then there's the propagator correction diagrams, which are trivial to calculate, the two-point function diagrams, but the physical interpretation is non-trivial. Okay, so let's look at the vertex corrections to the flip vertex. So in my notations, this is the flip vertex, which at leading order is proportional to the quark mass. So you get correction from this kind of diagrams. So here you have we have three vertices here. And if we want the total to be a spin flip we have two options. Either one of the three is a spin flip vertex, or three are spin flip vertices. If I take the case where all three are spin flip, this gives me a finite NLO contribution. The integral doesn't type. Integral is finite because all the spin flip vertices are proportional to the mass and not the momentum. So it's less UV divergent. But if I take the case where one of the three, and there's three options, any one of the three can be a spin flip vertex, I get a log divergent contribution. So I get a contribution which is proportional to the quark mass and a 1 over epsilon from the dimensional regularization. Here I have two energy denominators which go like k squared, and the two non-flip vertices which go like k. So this makes it a logarithmic integral which has a logarithmic UV divergence. So fine, I get a contribution which goes like quark mass times 1 over epsilon. This I absorb into a renormalization of this mass in the leading order vertex. So this is what I call a vertex mass counter term. So I absorb this into a vertex mass counter term, and the actual value of this counter term, at least the 1 over epsilon part, is the same as the mass counter term in conventional perturbation theory. Then let's look at the non-spin flip vertex. So this is the leading order non-spin flip vertex. So if I want to have a non-spin flip, I have two possibilities. I either don't have a spin flip vertex at all. So this is not qualitatively new. This is the same kind of thing that I already have in the massless case. So it's not very interesting. The other option is that I have 2 out of the 3 vertices are spin flip, and one of them is non-flip. But this is again a finite NLO contribution. The integral goes like it's d squared k, only one vertex proportional to k, and 2 energy denominators. So this is a finite UV finite transverse integral. So this is a finite NLO contribution. I don't have any somehow trouble there. Then let's go to the propagator corrections. So here I'm evaluating this kind of diagrams where I can have either 0 or 2 spin flip vertices. So out of these 2. And now I'm not considering this one because that somehow factorizes out. So I have 2 vertices which can have a spin flip or not. So of course the one with 0 spin flip vertices is just like the leading order, so that doesn't somehow change that much. The one where I take 2 spin flip vertices, so both this and this are flipped, it means that I get a contribution which is proportional to the quark mass squared. And this is a logarithmically, then this integral or this loop is a logarithmically divergent integral. So what I get is something that goes like quark mass squared times 1 over epsilon. So this divergence can be absorbed into the renormalization of the quark mass that appears in the energy denominator of the leading order Lightbone wave function. So this diagram, the leading order diagram, has an energy denominator which has a mass, and that mass, of course, gets a one-loop correction. So this is what I call the kinetic mass counter term. The kinetic mass being the mass in the energy denominator.
What object are you renormalizing? I don't understand how you can renormalize an energy denominator.
No, yeah, the energy denominator depends on momenta and masses. Sure. So there is a mass, and this is a mass I can renormalize. This mass gets a one-loop correction.
So if instead of Raycon perturbation theory, I was using a small s Raycon gauge, I'm doing the same. Would I have the same issue? So this seems to be.
Yeah, you have a mass. The mass appears in your propagator, and then when you calculate something with this propagator, then the mass gets a renormalization. Mass is renormalized, and that changes your propagator. I mean, it's one way or the other.
Yeah, but in covariant perturbation theory, you only have one mass to renormalize.
Yeah, so I will get to that. I will come to that. So this kinetic mass counter term. But now this is the problem. The kinetic mass counter term is not the same as the previous. The 1 over epsilon part is the coefficient of the 1 over epsilon is not same. So this is not the same mass counter term as the vertex mass counter term. Okay. In fact, the vertex mass counter term is the same as in covariant theory. The kinetic mass counter term here turns out to be different. So this is not a new thing. So this has been known for a long time. So Hydra and Jean, and also there's a very useful discussion by Burkhardt in terms of Yukawa theory, where the same problem appears. So what is the origin of the problem? Okay, So actually now in the way we are doing the calculation, there are two conceptually different masses. There's the kinetic mass, which relates energy and momentum. And then there's the vertex mass, which is the amplitude of the spin flip, which is related to the amplitude of the spin flip in the gauge boson vertex. So when you do a Lagrange, when you start from Lorentz covariant Lagrangian, in the Lagrangian there's only one mass. And this is why this is what you were saying. You do covariant perturbation theory. There's only one parameter, which is the mass, and that gets renormalized, but that's fine. But what we do here is that from this Lagrangian, we first derive a Hamiltonian. Now, the Hamiltonian has a mass in two places. It has a mass in the free term, the kinetic mass, and it has a mass in the interaction term, in the spin flip, the vertex mass. So it has a mass in two places. And now, after we have derived this Hamiltonian, which has two parameters, which are called mass, we then quantize
This is
the
because
theory.
you integrate one of the side fields. So, right, you have side pluses and minuses.
Yeah, no, this is, you integrate over one of them and this
is.
is.
Mass
Yes.
appears in the interaction.
Yes.
But it's still the same mass, it comes from the same Lagrange.
It comes from the same
Like
Lagrange.
you're saying when you renormalize it.
Yeah, when you the problem comes from the renormalization. So somehow Lorentz invariance requires, of the original theory, requires that they stay the same. But in practice, if you do this, the light cone perturbation theory calculation using a cutoff in K plus and a transverse momentum dimensional regularization, you violate rotational invariance when you rotate from Z to transverse. So your regularization in your loop integral violates rotational invariance. And this breaking of Lorentz invariance, the breaking of rotational, three-dimensional rotation invariance, leads to the vertex and kinetic mass being different at the loop level.
But so, again, if I'm just using what I'm using, just effective Feynman loops, covariant perturbation theory, the diagrams match one by one with icon perturbation theory once you're just integrating over that with time. But I'm still using covariant perturbation theory. I'm not touching.
So the question is how you regularize.
Yeah, the question would be why in that case would I need MV different from MK? Because in that case,
so the question is how you regularize the integrals.
So it's just about this K plus.
It's about regularization.
So if you were using
it's an artifact of the regularization.
If you're using Mandelstein diagram, for example, for K plus instead of the cutoff, would you restore MV equal MK?
I don't know.
I
don't know how to think. I don't know how to think of Mandelstein diagram. But here it's a question of this scheme, regularization scheme, where the K plus integral has a cutoff and the transverse integral has a dimensional regularization.
So this has nothing to do with the Hamiltonian. I would have the same in covariant perturbation theory if I was using the same.
I guess so. Let me actually ask this question. So when your issue arises on the previous slide, if you could go back one slide. So the diagram at the top, do you do the instantaneous parts of the quark and gluon?
So this is fine. So
this is one of your bullets.
Yeah. This is one of my bullets. So
the normal covariant Feynman diagrams, like a perturbation theory, one diagram gives you one Feynman diagram gives you a different light cone diagram. Right? It gives a diagram that almost has, and then instantaneous parts. So you shouldn't compare just to that diagram.
No, of course, all the sum of them.
But the sum really, there is a
diagram by
diagram. I will tell you. I will tell you if you stop asking the question. Let me answer.
So if you calculate gauge invariant physical quantity, this diversion should disappear, right?
Yeah, exactly. But it's a technical question issue of how you regularize your loop integrals, and whether this regularization preserves the symmetries of your theory.
Okay. Well, you can choose not to as long as you calculate.
Yeah. So there's two. So this is why. So you can choose. There are different choices that you can get around this problem, and they have pros and cons. Yeah. Well, in the end, when you calculate the physical quantity, you get a physical result. It's just a technical question of how you organize the calculation. Okay. So this kind of regularization violates rotational invariance, so leads to vertex mass being not equal to kinetic mass at one loop level. Okay, so there are different options that you can think of how to deal with this. One of the what was somehow in this Hydra and Zhang, what they do is that they use another regularization method, cutoff in K minus, which actually does not have this problem, but this is completely but this is
okay minus. So how do you?
That's when I say K minus cutoff, I mean that that you regulate K squared over K plus. You set a cutoff requiring that this variable is less than some UV cutoff. But this mixes up transfers and longitudinal, so it's very inconvenient.
So this is exactly what they're using in PF.
I don't know. So somehow the regularization methods used by these guys, they see that they keep two masses the same, but they only look at the divergent parts. So you can see that you can see this for the divergent parts. In order to actually do the full calculation and get the finite part, it's completely impossible with that regularization scheme. So it's hard to come up with a regularization scheme that actually is simple enough that you can actually calculate the finite parts. The other one, which I will add, okay, so let's go to this one. What Yuri was referring, and I won't have that much time to say this will be a separate talk. What you can do is that you can take the instantaneous normal ordering diagrams, which is what also come from if you generate these from covariant theory. You also get this instantaneous normal ordering diagrams. So diagrams where, for example, you have this. So this is an instantaneous, and then this kind of glue on that goes like this. This kind of funny diagrams. So in our regularization scheme, this diagram is just 0.
There's also the one with the glue on.
Yeah, there are other ones.
They're also 0.
Yeah. All of these are 0 in this scheme.
Because they're transverse platform?
Because they're transverse platform. Yeah, it's a scaleless transfer. Transverse momentum indigo is a scaleless indigo, which vanishes in dim rate.
Your scheme was
even with the
transverse dim rate.
Transverse dim rate. This is what I said. Transverse dim rate.
How do you get the mass? The mass could distinguish what is infrared and infrared.
No, it's still 0. It's still 0.
So then it doesn't solve
it doesn't have an energy denominator. It doesn't have an energy denominator, so that's why it has to be 0.
So when
it's a scaleless indigo because it doesn't have. Yeah. It's a
So I'm sorry, when I remember myself, calculated running company corrections, we initially missed those diagrams and we couldn't get the right constant term, and we actually included them and they were not 0. So
it depends on your regularize. Depends on how you regularize. I mean, there's no energy denominator.
We use transverse dim rate.
There is the photon you do proton type one, which shows on this, right?
What? Yes. Say that again.
I mean, you have the one from, because this is just the line, but you also have the photon splitting to proton type one.
Yeah, but this is somehow here.
Yeah. So you have one energy denominator for that diagram.
Yeah, but this is just the leading order energy denominator. It doesn't depend on. It doesn't depend.
Okay,
let's say
sorry.
The energy denominator. You don't have an energy denominator which would depend on the mass. Depend on the momentum of this gluon.
No, sorry.
So when you integrate over the transverse momentum of this gluon, you get 0.
There is a known problem that if you just open Brodsky Lappi and use their Feynman rules to write an expression for this diagram, you're going to get some singular garbage. And you really have to start with Feynman diagrams and do that careful integral.
I know. It is a known problem, but this singular garbage is 0 in this regularization scheme.
Oh, so what I'm saying, what you're saying seems to contradict what I remember. We did 10 plus years ago with Heidelberg, where those diagrams were very important. Also in the transverse dimensioning. So yeah, well, no.
Oh, this was very late.
So the transverse dim rack, they were essential to give us a constant. So
but I think probably what you are doing is something related to what I have here, point 3, which I'm not going to discuss. So if you actually take these diagrams and you somehow, in some you can fiddle around with them, and if you somehow combine these diagrams with the loop diagrams before you integrate anything, so you're not integrating yet, so you don't need to regularize yet. and then you somehow smartly identify split this into different parts, you can actually do the calculation in such a way that you explicitly keep the two masses the same. And Guillaume's talk with hard probes has a little bit more detail on this. I didn't want to go into that.
Actually, I take my comment back. We have a slightly different diagram. In the loop, if we have an instantaneous line in a loop, that was also 0.
Yeah.
It was more like you need an instantaneous view, understand this fair.
Oh yeah, that's different. That's different. So somehow there's a way to somehow taking these into account, shuffling, reorganizing, then identifying a certain part that you have to treat in a certain way. So there's a way to get around this, which I'm not going to discuss here. What I will discuss here is this option 1. I very briefly discuss this. Is that to regularize as before, and just accept the fact that you have two masses, and you need another renormalization condition to separately renormalize to the physical value. So, and of course, the physics is the same, so both of these lead to the same result. So you need two mass renormalization conditions. One condition is kind of standard. We want to use a pole mass scheme. In practice, so the pole mass scheme means that for a mass, for an on-shell propagator, in covariant theory, you would say that for an on-shell propagator, the mass correction is 0, or somehow the mass has the physical value. In practice, the way you do it in this calculation, in the practice, the way you implement the pole mass scheme is that you look at this diagram, and when the leading order energy denominator goes to 0, you require that the mass correction from this diagram vanishes. So somehow you subtract essentially from this diagram, you subtract the value at energy leading order in the limit when the leading order energy denominator is 0. So this is kind of standard. It comes the exact formulation of what the pole mass condition means happens in a slightly unusual way, but there's no mystery in the physics. So this determines that you can use this to determine the kinetic mass counter term. And this is why actually the gamma L, the longitudinal polarization is easier, the whole calculation, because for the longitudinal polarization, this is the only mass renormalization you need, because you don't really have you don't have the same vertex correction diagram. So FL this is why we already have a result for FL, because this is straightforward. The other condition, what we did is that we broke rotational invariance. So we need another condition to restore rotational invariance. So one way to do that, and of course you can write this in a more general way. I will try to somehow. This is the physical argument that actually led us originally to this, and this is very much like what Burkhardt was doing in Yukawa theory, like 10, 20 years ago. You need to calculate a quantity which you know is rotationally invariant, and then require that it's rotationally invariant. So, for example, you can calculate at one loop level the decay rate, the decay amplitude for a time-like virtual photon. So you calculate the time-like virtual photon to quark anti-quark at one loop. It's the same diagrams, it's just a time-like photon. And then you put the final state on shell. So you're really calculating time-like gamma star to QQ bar at one loop. And the loop diagrams are the same. So you get the same mass divergences. And then you just require that the decay rate for a longitudinal time-like photon is the same as the decay rate for a transverse time-like photon, because here the physical situation is rotationally invariant. If you have a time-like virtual photon, then the distinction between transverse and longitudinal is just a choice of what your z-axis is. So rotational invariance it requires that a time-like virtual photon has to have the same decay amplitude in the transverse, and the transverse and longitudinal time-like virtual photon has to have the same total decay rate in the QQ bar.
Well, you can have it addressed.
You can have it addressed, exactly. But this is why it has to be time-like. For a space-like, it's really physically different. For a time-like, you can go to the rest frame, and then there's no difference. So you calculate for a time-like gamma star. Then you go to a particular value for the transverse mode, and longitudinal moment. Right? So you go to the final, go to the kinematical configuration where this is on shell, so where the K minus of the final state is the same as the K minus of the initial state. So you go to a particular value of the transverse momenta and form fractions. So from that point, you get a condition. On this condition, you get an additional condition, which fixes the vertex mass counter term. And it, in fact, turns out that this condition gives you just a conventional covariant perturbation theory value for the vertex mass counter term, for the mass counter term. So this kind of gives us credence that this is the right, that this gives the right result. In some sense, the problem here is that it's kind of easy to, you know already, once you realize what the problem is, you kind of know what the result is. The kinetic, the vertex mass is the conventional counter term. The kinetic mass you can get from the pole mass condition, so you kind of know what the correct result is. This really just serves as a check that you really, this is the formal way, gives us an explicit way to calculate the result that we know already is the correct result, because it's the same as a conventional perturbation theory. So that's reassuring. So, and again, as I said, if you're not happy with this, then you go to option 3 and fiddle around with the normal order diagrams, and you get the same result. Okay, but that's discussing these would be a topic for another talk. Fiddling around with these also lets you keep the gluon massless. If you do it this way, the gluon also gets a mass at one loop. Usually you normalize away. So
Sorry, what? Where does the gluon mass come from?
it doesn't. Well, not in these diagrams, but the gluon mass comes from calculating this diagram, where you have a massive quark going around in this loop. This gives you a contribution which is a gluon mass, one loop gluon mass. In this regularization scheme, it gives a non-zero contribution, which is a gluon mass, which you have to renormalize away by a gluon mass counter term.
But once again, if you go start with Feynman diagrams, do everything there. And
Yeah. So then, if you start with Feynman diagrams, then you have then you somehow have the corresponding instantaneous diagrams here, and then you arrange them in the right way, and then you can you're fine. And so if you want to see equations, go look at the Guillaume's slide from Hartford. So there's another way to do that. Anyway, so as I said, I actually do have a finite result for FL. It's a long equation, not particularly illuminating, but we have a result for FL. We're still working on FT for this. So instead of conclusions, so just to things that are still to do, actually do a fit to Hera data with the NLO impact factor, with a leading log or next to leading log evolution equation. And then there are some issues about issues that I kind of touched on, how to match the NLO evolution with the NLO cross section. That one, there's not an explicit formula that would still. Well, let's say there are issues that one needs to think about when you actually calculate cross sections. So related to what the evolution variable is, and this evolution variable, this is of course related to what this kinematical constraint is, and how what the integration limits are, and these kind of things. There's loop calculation ongoing, doing the same for massive quarks, and of course there's lots of other interesting physics that I did not discuss here. Thank you.
Thanks for finishing early. We have plenty of time for questions.
So you essentially, you started by posing this. Started the last part of your talk by posing this charm F2 charm issue. So you don't know whether this calculation that you're doing will resolve.
No, I have no idea. It's just an excuse to do a hard calculation, right?
Okay. Can I then make a comment about spin flip terminology?
Yeah.
So that term looks like a spin flip if your spinners are implicit bases.
Yes.
If you choose your bases and your spinners would be eigenstates of transverse spin, this would not flip any spin. It would be a diagonal term.
Yeah.
That's why Guillaume is right.
Yeah,
You don't just call it spinning.
I fully acknowledge Guillaume is right, and somehow talking about it spin, calling it spin flip, I know it's incorrect. Just a short.
Like you do it.
I do it anyway. I'm fully aware that it's incorrect.
It's a helicity.
For me,
That's the same.
there's two components, and somehow I think of them as spin.
This is actually like a simple way to argue why transverse spin dependence always comes with a mass. Because transverse spin dependence corresponds to helicity basis, looks like a flip. And the flip helicity on the mass.
Yeah. In some sense, in the Lorentz structures, I think, I assume, I haven't really thought about this, but the Lorentz structures, I guess, somehow, in some sense, this is the Lorentz structure that couples it. It has one couples the transverse vector potential. So maybe this is, I don't know. Anyway, yeah. So that's good.
We break for lunch, or you are known?
Yes. So we have a talk at 2:30.
Yes, I guess we're gonna have Renault's talk at 2:30. The discussion.
Yeah, I guess so.
Yeah.
So hopefully we're also planning a discussion in the afternoon.
Oh, I think we had the discussion already.
We have already discussion.
And there was 2 hours of discussion.
All right,
Yes.
we'll play it by ear. We'll just reconvene at 2:30.
Oh, nice.
This one, the comments.
You bring the same traditional restaurant
What's the
for lunch?
we don't have to go there, but if you want,
I don't know.
there's so many choices.
Oh,
We went to the Mexican place last night. I mean, if you really
whatever you want to do, that was fine. Yes, that's good. If you just be careful not to hit so much that you can't walk.
if you go for a burrito,
Yes.
then you can't have one. That's why you go for tacos.
Or get-
Yeah. I can meet them like, I don't know, 5 to 10 minutes and.
Just around here.
Yeah, maybe later, and I'll think of the restaurant.
I'm having lunch.